Chuck. So, without further ado, Julian, if you'd like to come up. Julian is the rehabilitation manager at Wessex Water, and he's going to be talking about a client's perspective of assessment. Julian also served as part of the UKSTT up until a few years ago. Thank you.
Right, well, thanks Chuck for warming them up. I don't like the term rehabilitation manager. It makes it sound like drugs, doesn't it? But at the end of the day, what we're doing is important in saving our networks, which the Victorians gave us, and this stood the test of time very well. Now, I'm not here as an academic or a consultant. We have lots of great consultants around us who work with Wessex, and I'm just here to give a company perspective on what we do, and if I'm a little bit flaky about some of the concepts, it's because I haven't really done my homework as well as I should have, so I apologise. Wessex Water is probably one of the smallest water companies down here in the southwest. We actually have two other water companies embedded within our area, Bournemouth and Bristol, so we only serve about 1 million people with water, but we serve sewage to 2 million people. And you can see all of the statistics, as you'd imagine. But I'm here today to talk about sewers, and the red comment here is that out of our 35,000 kilometres of sewer, some 70%, 75% are going to be 9-inch and down. So those are the sizes we tend to concentrate on. And when Chuck was talking about the size, he was relating to the fact that in the United States it's 8-inch pipes, and we're 9-inch pipes. Okay, and that was what it was about. But we do have a few in Chippenham, a few 8-inch pipes. I'm sure Thames do, yeah, and Severn Trent as well. So he went away and he redesigned the device for us, and I'll come to that at the end of the presentation. So we're here at Wessex doing all of the things you do with structural attack as hydrogen sulfide, which on concrete, which is a major problem to us. We're rising mains outfall, and we have anaerobic conditions forming, and high parts per million turn into sulfuric acid. Serviceability for root infestation. CIPP lining, for example, is a good way of dealing with that, and KT have done a lot of work on root crushing factors on CIPP, which is also interesting. Infiltration, which is a big problem to us. We have a consultation through various parties with Thames. I know Thames have problems with infiltration. We do, Anglian. Not so much the companies up north, Northumberland and Yorkshire. I don't think they have. They tell me they don't have such a problem. When you're having development, we have unscrupulous ready-mix drivers putting their concrete in our sewers. I'm sure you do, so we've got robotics to take all that out now. It's all keyhole surgery, and nature's concrete, calcium carbonate, calcite, can be major problems as well, and then strange things like rebar. Now, I'm not here today to talk about how we analyse our sewers. I'm on the contracting side of Wessex, and AS&C, our clients, they do the analysis. There's a paper in your pack from our director, Matt Wilden, talking about risk and consequence, maybe moving slightly away from the old critical sewers idea in the SRM manual, and it's serving us well. We have found that we're not necessarily reducing our collapse rate, but because, you know, at the end of the day, we've got this concept that sewers are moving from a grade 4 to 5 at around about 45 kilometres a year, and if we're only replacing 25, we're leaving a legacy for our children, you know. So read that paper if you're interested in those concepts of risk and consequence. So the Americans invented CCTV back in the 50s. This young lady, I'm sure, retired a long time ago in Axbridge near Cheddar. That's one of the first cameras. Of course, up until the formation of the water companies in 1974, it was all agencies, yeah? So she would have been working for Axbridge. And we do all the things that you do with the SRM manual, MSCC5, coding the sewers, grading them, and then repairing them. We tend to do grade 5s and associated grade 4s, which are close to grade 5s. so that we don't annoy customers by turning up all the time, you know. And then in the United States, I'm sure that Chuck will tell you about granite, etc. Is it granite? Q's? It's Q's. Okay. So when it comes to the SRM manual, we were instrumental in 1979 to 1984 in doing the design calculations for the GRP linings. We lined some sewers in Weston-super-Mare, we loaded them by Kentridge to destruction, and then we worked out the mathematics. And I was at the No-Dig in 1987 in London, and Los Angeles were there, and they were the first ones to pick up the SRM manual, and they were really pleased at what they'd done, the hydraulic side and the structural side, and they presented some great papers there, I remember that. So coming towards the end of my career, I've got memory. So, what do we do? Well, we've got 3 of our own in-house CCTV teams. We keep locked with a framework with 5 other companies every day of the week. So we've got these IBAC and IPEC and cameras, etc. The siphons, just like referred to earlier, Chuck, the trace here is the underside of grease stuck in the roof, and that is a trace of road grit stuck in the floor, and there's the flow-through zone in the middle. We've been using ROVs for outfalls from sewage treatment works, and also some of our tunnels which have become submerged where they carry rising mains. We've had to drain them out, but we first send in ROVs to have a look, and then, as John was referring to, we do all the gross metal loss, etc., to work out longevity of them. And then we've got lateral launch cameras within the company. They're coming of age now. And finally here, this is a Rangedale boat from Australia, which we'll talk about, and that's 2 meters long for doing large diameter tunnels. We do use lasers quite a bit these days. We use them primarily for ovality checks on plastic pipes for sewers for adoption, no more than 6%, and we can reject them if we get more than that. We are going to be using them for sizing rising mains. I have my colleagues in the back here on site who've been with us for many years doing our framework contract. They're putting in their first properly designed rising main liner under the new draft ISO 11297 in a couple of weeks' time, so that's exciting. And then we've also been able to look at 3D lasers for measuring voids, where we have some sand caves on the south coast outside of tunnels, etc. So what's new to us? What's exciting? So first of all, it's really million point cloud. This particular instance here is in Bristol. This is the Jessop's floating harbour. It was cut in 1809 as a relief to the River Froome in Bristol. Actually, it was dug by Napoleonic prisoners of war, and it stood the test of time. These walls here are supporting the Mercia mudstones Coiper Miles, which are a weak rock, and we've got a sewer which comes out just there. Now, the wall has recently been moving away, and the wall isn't owned by us, but the sewer is, and so we want to protect our asset, and so this is relatively cheap now to have models set up and return periodically to measure if the wall's moving. And actually, what is moving the most is that now that we've taken the flow away from the outfall, we've got the second highest tidal range in the world on this river in the Bristol Channel. It's up to 13 metres a day. It's only behind the Bay of Fundy in Canada. And it deposits massive amounts of silt. And where it was eroded away, the silt here, is now been picked up by the later scans to show that it's come back. It's a very useful method for us. We took this on recently at the conference centre here, where all the tourists meet, and the Liberals, I think, were there this week, on Bournemouth Coast. This is a hill coming up at the back. And recently, the hill has started to slip in this zone. So our sewer is running along here. It's 2 metres in diameter. And they wanted to put some Larsen piles in, some anchors going back into land with duckbills on it, another pile of Larsens, tension, and lock the whole thing together. But our sewer was in the way. So we've done a million point cloud. Here you can see the shaft. Here's the tunnel. And then we triangulated it in with a terrestrial survey, and we're able to set out the tunnel so that they could fire their anchors across the top without hitting us. I'm sure Thames, especially Thames, would have problems like this. And I know that Mark Lusher has been doing some good work the same, you know. So, not saying we're the first, it's just a very useful tool. So Bristol, we started tunnelling on the regional valve scheme. It was dreamt up in 1898, didn't come to fruition until 1951. And there's 40 kilometres of tunnel down going from 2 metres here up to 5 metres on the coast. And the insurance companies really were saying to us, and Yorkshire, why would we want to insure your assets if you don't know what they look like? And to be honest with you, it's been very difficult to get vehicles through here. Certainly when it comes to the crawlers on cameras, if you get maybe over 100 mil, 150 mil of sediment, they struggle. And so we wanted to see if we could find a floating platform to go through. So we came together with Water UK, and we were asked to put together a document which gave all of the methods of surveying, maybe a bit of cleaning as well, large diameter conduits. They didn't want the word tunnel, they chose conduits. This document is available from Water UK, and it was signed up by all of the water companies, as you can see. But what primarily came out of this was the fact that we knew what platform we wanted, a floating platform, either Rangedale or the one from Clear Flow in New Zealand, now purchased by Red Zone. And it was going to cost us millions to get it into country. We did a tender and we couldn't fly it over from Australia. So by working with our colleagues here, especially Yorkshire Water, who did the first survey, and UU, we were all able to bring this vehicle over. Here it is here, the profiler, and it does laser, it does photographic survey. It's not continuous CCTV, it's instantaneous flash-driven photographs, and below it's sonar, as you can see here. We deployed this in the Weymouth Tunnel, where we've had lots of hydrogen sulfide corrosion. You can see the vehicle now moving away from the shaft, the laser here. And this is in a tunnel around Bournemouth, where you can see hydrogen sulfide attack and another pipe in Weymouth. And it's relatively good value. Its results take time to come in because they have to be sent back to the United States, Red Zone, to process them. And we have a process of using the vehicle over the next year. We're setting up projects which include CCTV. We're not discounting CCTV. It's about a third split with man entry as well, to look at our tunnels over the next 3 years. And an unusual thing that came up on the Weymouth Tunnel is that we had some osmosis of our GRP linings. So you can see wicking of the glass here and the GRP. This is at the leading edge, because long-term water and glass don't like each other. And we had to replace several meters out of every manhole because of this delamination, as you can see. This is a photograph from Yorkshire Water of the E-Shot Tunnel. They hold the record with the profiler so far of around about 4 kilometres in one pull, which I think is tremendous, and takes about 4 or 5 hours. This is Staffordshire blue bricks, so the light reflection isn't so good. Most of our sewers obviously are concrete. And you can see here, as the boat is going underneath, the laser is disappearing up here. And you can also see the boat, it's the form of the boat here, and the outriggers on each side to balance it. Okay? No sediment there, so that looks nice and clean. We used it at Bournemouth on the first survey, and we did 12 lengths and 8 kilometres. We did 3.3 kilometres with 4 lengths with sonar. Unfortunately, there wasn't enough flow to use sonar all the time. There was very little sediment in the tunnel. We just picked up some 28 cube close to the Holt sewage treatment works, and we're able to now quantify that for cleaning. And the average depth of flow was 300 to 400 millimetres. The interesting thing is about the vehicle that it's got a metal cage on it, and at times we had some storms come in, and the tunnel filled up within 15 minutes. The boat was crushed against the roof, but we just held it on station. It wasn't damaged because of the reed bar on the top, and then off we went when the flow dropped down. So that was useful to us. To date, we've our longest pull is 1.6 kilometres, sorry, 2.7 kilometres, but we're going to be doing a 4 kilometre pull in the spring. Project duration 2 weeks, so that was excellent. Now, this is a shaft. Panorama, which is the facility for lowering down manholes to take photographs and mapping them, can be done. We've got a few other ideas. But you can see this terrible hydrogen sulfide attack. And it was built in 1969. And here is a high-level flow coming into the shaft, into a vortex. I'll go into this in a moment, but this vortex is not working properly. The flow is dropping down, and the vortex is not formed to break the velocity of the flow as it enters the tunnel below. Overall, we found that we had, this is a premature slide, should come at the end, but we had several sections where we picked up bad hydrogen sulfide, and I'll come back to that. So as you can see here, close to the shaft, the hydrogen sulfide at 54 parts per million continuously has eaten away the concrete through the secondary lining into the primary lining, and it's in a state of collapse. So what we do is we carefully send in some men to do coring. We take the cores and do a petrographical analysis where we cut the concrete up into thin slices and put fluorescent dye on them. And then we look at them in detail for the conversion of the portlandite. We're looking for the formation of thaumasite and ettringite, and then from that we can work out the longevity by crushing the concrete. We can work out longevity of the lining as an asset tool, and we can go back to the board and ask for money to replace. This is the outturn. As you can see here, we've added a factor of safety, so it's not very clear, but we've added a factor of safety of 2, and the red zones in those upper parts where the vortex wasn't working went down to 1 year longevity. So I went last week and scared the arse off at the board, and they gave me £1 million. Now, the interesting thing, I'll just touch on this because I'm quite proud of this. Before 1974, it was the agencies, the same in London, I expect, and those engineers were brilliant engineers. And we had a guy called Bernard Smithson, who was a hydraulics engineer, and he invented the energy dissipating vortex. So this is the concept here. This is a small one that we're putting in Bournemouth to replace the one you saw corroded. But in reality, we've got these 90 metres deep. We've got them at around about 400 mil diameter, and they take massive flows. They drop it 90 metres underneath Bristol into a large tunnel. But what he found was that when the water was going down this drop pipe, full bore, we were getting, we had a duckfoot bend down here. We were getting cavitation on the duckfoot bend, and it was being destroyed very quickly. So he put this vortex air suppression pipe, this U-shaped thing above, like so. And as the water now goes in, it has to spin and leave a core in the middle, and that stops the cavitation down here. When the storm in combined sewers comes up and covers that pipe, all the water rushes down and you lose the vortex. Yeah? So these have been really successful, and Hydrobrake have taken that on, that concept, designed by him in 1955 in Bristol. And it's an interesting story also, if you've used Hydro's Grit Kings, I think they call them, yeah, where they, dynamic separation of material. He actually invented that, or discovered it, while he was drinking a tea in a cafe in Bristol. And he was stirring a black tea, and he noticed, in those days there were tea bags, yeah? So he noticed as you stirred it, all the tea leaves went to the centre and down to the bottom, yeah? And so he invented the Grit King based upon that principle. There were about 4 of them put into Bristol, but there were more put into Chicago and New York. And when I was a young engineer, above my desk there was a plaque from the people of Chicago saying thank you for sorting out our problems. So, what do we do? Well, we're big in GRP lining as well as CIPP. These linings are from Amianti in Poland. We can get them from Hobas and Channel Line in Dubai. In their wisdom, the EU have just allowed, I guess through their Monopolies and Mergers Commission, Hobas and Amianti to get a link up. So we're a bit worried about pricing, but we'll have to see what's going to come about. So, all of these large diameter tunnels, how do we decide which ones we're going to spend our money on? As an asset tool, yeah? We've done a lot of work with Roland Woniek and Bert Bosler at IKT in Gelsenkirchen. You saw Chuck's got a connection with them as well. I'm sure you have. Dr. Olivier Thibault of Eau de Paris invented the extensometer, this device here, as you can see. It's something that was used by us for the first time in England. We were pretty confident it would work because it had worked in Germany and in Paris. We even spent a little bit of extra money on some Armco analysis. We didn't expect it to work, and it didn't, frankly, because the coating on the Armco would all have to be stripped off to understand the stiffness of the material. Okay. So we had a tunnel in Bournemouth. The lining was a flexi-lock lining from the 1960s with no bolts in it. It should never have been built in a sand lithology, and it's best suited to the over-consolidated London clays. London clays are the best material in the world for tunnelling. I've done 25 years of tunnelling, and I know. But in the London clays, the ground squeezes on, and so it's best suited to that. Wasn't suited to us because, as you can see, at some point it got hydraulically surcharged and the plates were pushed down. We lost some sand at this point, so we didn't know too much about what was happening on the outside. There's one of my young engineers with an endoscope looking out there, as you can see. The flexi-lock plates ran out in the 1970s, and I don't think they've been used extensively in Wessex. We are doing some analysis in Bristol to see what it looks like. And here's the machine. So this is my engineer at the back, Nathan, with the German guys. And what the machine is doing is, it's got a ram, and that ram will create a force of up to 100 kilonewtons. It won't overstress the lining. It's got a device to stop it. And these three extensometers then measure the deflection in the lining, okay, so that we can get an understanding of its stiffness. So here's the concept. Pushing out here and here, and we're measuring the deflection here, getting the global stiffness. It's done every 5 to 10 meters, and then the information is here. So you can see 3 of them. They push out. All the data's collected, and then we take cores. So we take cores and we crush the linings. Actually, these flexi-lock linings will come out at 65 newtons, which is really good. So the actual linings weren't a problem. It was then an understanding of the geology behind. And between the shafts, 220 meters, we took all of these calculations. Now, that was the bit in the middle that was a problem. Visually, I think you'll agree, it didn't look good as an engineer. The rest of the tunnel looked really wonderful. But when you actually did the calculations either side, they turned out to have less stiffness externally in the geology than we had in the defective areas. The reason for that later on we found is with the endoscope that the grout had come up to guts level on the extradossadil tunnel lining, and that was giving us this stiffness here, increased stiffness, and reduced stiffness on these 2 areas over here. So on the basis that this part here and this part here are probably the same, we lined the whole section of tunnel. The work, the mathematics was done by Leibniz University on a finite element model, as you can see. And again, people like Mark Lusher, they're Thames, they're doing this all the time. Okay. So, CCTV, we do hundreds of kilometres a year, and everybody has to sit down and they have to code it all. It takes a long time, and we're worried about government proposals for road pricing this when we're on the road, etc. So we've started to look at automated fault detective algorithms, and we've been working with some colleagues from around the world, and they brought vehicle recognition of number plate technology into the sewers. Yeah? What we do basically is we take the USB out of the camera or the drive and put it into our computer algorithm, and it pixelates, applies filters, and identifies the faults as we go. I'm not an expert on this, and I can't remember exactly how to explain it. But it's a localized regional video frame using GIST features, if that means anything to you. Random trees are then used to learn a classifier to detect normal and fault images and differentiate between them. It's otherwise known as machine learning via trained random forests. Now, what that means is that the pixels pick up all of this. They can figure out infiltration problems, serviceability, structural, and on our first run, we had a success rate of 92%. I'm having meetings with them in the next couple of weeks, and they tell me that it's close to 100. So on 2% of the occasion, the computer's going to say to me, Julian, you're going to have to look at this because I can't figure out what's going on. We think that's pretty good. What does it mean for us? Well, we can take maybe one of Red Zone's autonomous vehicles that will drive itself. We can go to our manhole in Clevedon Road. We can lift it up. We've got 30 minutes under the road pricing, whatever. I don't know, it's not been decided yet. We drop the camera down, they go in the cafe, they pick the camera up the other end, we take the USB out, put in the algorithm, and we don't need people to code sewers anymore. Does that sound good? So, watch this space, that's going to be coming up in the next 8 months. We'll probably do some press release on it. I'm here to learn as well, so if anybody knows anything better, please tell me afterwards, right? We don't have all the monopoly on all the best ideas. ElectroScan, we met in 2012, and it was organised by Wessex Water, and Chuck was there with his system, which we'd known about as 1241 for a long time, but Chuck had brought his intellect and all of his software capabilities to it, and made it into a really holistic product. But did it work? That was the question. So we've got a lot of infiltration in the south, and as you can see here in the AMP6 period, we are looking at spending around about 40 to 50 million pounds on excluding it from our sewers. The obvious reasons for that are that we have to pump daisy chains between villages, so there's the cost of pumping, the wear and maintenance on the pumps, premature initiation of CSOs, and it reduces the amount of development that can happen because it takes up the capacity in the sewers. Okay? So we had, thanks to on-site, Simon Bayliss and the team, who worked with Michael Moulin at EPROS, later Trelleborg, to design epoxy linings for exfiltration. We all know that CIPP, polyester linings, can suffer post-exothermic contraction of the lining, which we try to reduce by making sure that we cure properly, we don't shock the lining, and we bring it down slowly. But at the end of the day, these linings were needed because they stick to the substrate with something up to 2 newtons per millimetre, which is fantastic. They've been a huge success for us. Here is Don Ridges of Thames Water. Yeah? Oh, cool. And there he is testing it in Dusseldorf with EPROS back in about 2009. So we had the solution, but we didn't have the diagnostic tool to know which assets we really should be mending. Don took it one further step on, and it developed the CPA 308 test for resins. We use this all the time now, and we make sure that we only use resins that pass, and we test every line of short-term flexural modulus, and we have all the lab results for the EL50, so we've got all the quality, the QA sorted on CIPP as far as we're concerned. So ElectroScan came along, and we took them to Cernabus over Stratton Coombe-Flory. I hope that we added some value to the vehicle at the time. I've never seen so much infiltration coming in at Coombe-Flory here on Exmoor. And we had an independent consultant do a report, And so we stood away from it, and they said that it definitely worked, and it showed up where the infiltration was coming in. We paid a little extra to Chuck, and he gave us the gold standard where you can work out Simpson's area, Simpson's rule area under a curve. Just one thing, Chuck, at the time we were looking at specifying our own head of water over the sewer. What do you take a standard now? Was 300 mil, isn't it?
Yeah.
Is it still that?
Yeah, it is. And we're working to vary that, so we can go into a lot of different cases.
So we put our head on top of the water with the calculations, and they conclude they actually found it difficult to find any disadvantages. I've got to say, credit to ElectroScan. From the only caveats, as far as we're concerned, that you've got to surcharge the sewer and flood it while it's surveyed, and so that meant that we had to watch out for CSOs that we didn't infringe and prematurely spill, and we didn't flood any customers out. So here is a simplistic diagram of what Chuck was talking about, and we tried it in Cern Abbas. So Cern Abbas had a dry weather flow exceedance at the works by quite a bit, and our colleagues had designed a £2.5 million construction of storm tanks to get us back into favour with the EA. Once we lined 550 metres by for £100,000, we found here, you can see the graph before and afterwards, there's the green consent line, way above it before all the time, and afterwards we dropped the flow by 13%, and now we're underneath it. So they cancelled the storm tanks at £2.5 million. And I think that's one of the things that gives me the buzz the most with CIPP, is how many millions you can save by some careful asset analysis, you know. And those are the figures there. We carry on using ElectroScan. We used it last week in Stanton St Quinton. Here is the data. So you've got the small leaks, medium and large leaks here. And then you can compute the litres per second or litres per day, and Chuck will also do in gallons. We don't tend to deal with imperial too much anymore. But anyway, great breakdown of all the sewers, and then you find out those are the 5 worst ones, giving you 60% of the estimated flow incoming. And that's where we would spend our assets. So overall, it works for us, and we've been able to please the EA about dry weather flow exceedance as well. I won't go through all of this, but it's all very impressive. Now, one thing about, I don't know if it's the same with you guys, but I'm in a bit privileged position because often when somebody invents something, they come through my door first to try and sell it. And I guess at least half of them I have to tell people in the nicest way they don't need inventing. But when we were out there, Chuck had a great engineer called Andrew O'Keefe, and I was asking him about this line here, which he called the noise, and that distance between the base and the top of the noise. Yeah? And he told me that it varied depending upon the material, host material, the pipe, clay, concrete, etc. So, doing my usual thing of being a bit off the wall, I said, well, if I have a concrete pipe that's corroded, and I power wash it and take away the latents, and I get back to a good substrate, and then I put a laser through, and I can work out the diminution in the wall thickness, what I've got left. Then if I apply the geostatic and hydrostatic loadings to that pipe, if we took a series of cores through concrete pipes and crushed them, could we correlate that to the porosity and density of the pipe that you can discover through that noise? It all seemed plausible. We went to see a doctor of concrete at Bath University, and he was really quite excited about it. But you know, in our business, there's so many things to do. We just haven't got around to developing this tool yet. It's a great PhD for somebody. We will do it. We've decided today we will do it. But the interesting thing is, it's not just hydrogen sulfide attack, diminution, but it's also sand attrition. If you look at this piece of pipe from Bournemouth. See the invert there, we've taken out, it's the invert piece. It's all been worn away by sand eroding it. Well, there must be a lot of that in Britain, and even more in Florida. Yeah. So I think it could be a tool for the future. Right, well, thanks for listening. I hope that some of it is interesting. I wasn't telling you in a sock eggs. But if you've got any questions, you can email me. And we've put some papers in just so that anything I didn't cover today you can take away with you. Okay? Thank you.
Yeah, welcome.
Thank you, Julian. So, good. John, you've come up. So we're going to have about half an hour set aside for questions and answers for all of the talks that we've had so far. So I would like to invite you all, if you could, whoever's got a question, raise your hand, I'll ask you for your name, and then if you could say your question very clearly. So I will start off with the first question, if that's okay. So, John, we talked about condition assessment, and we looked at how you're using other, loads of different ways to find the condition. Now, on the asset records, which the asset owner provides when somebody does a search and they're looking to do some intrusive work maybe, should there or is there a condition report that maybe you've done and you've said that this area is in a poor condition or that it maybe needs addressing? Is that given and put back on the asset record so that if anyone is doing any intrusive work, that they might know to be extra cautious?
I'm not sure of the answer to that,
Okay.
to be quite frank.
Would you think it should be?
Yeah, clearly, the agglomeration of information against particular asset records is very important. It's very important if we're going to do an assessment to be able to pick up all of that information.
Yeah.
And a lot of it goes back a very long way as well. So yes, it can be done.
Okay, thank you. Any questions to any of the guys, or more particularly on John's presentation? Any at all? No? Okay, fine. We'll move on to Charles. Charles, very good presentation about the cast iron. I'll invite questions out to the audience at all.
Sorry, can I just ask a question to John, actually?
Absolutely, yes.
You gave a figure of £3,000 per...
Yep.
Is that just your arbitrary figure? Where did you get the number from?
Somewhat arbitrary. I actually did have a specific figure for the average cost of repair.
Yeah.
But on top of that, most water companies will allow a figure for all the other associations with the particular event. So there will be an environmental impact if it perhaps delays traffic. There will be other things like reputational loss and so on. So you'd be actually getting a figure for the average cost of repair is relatively simple, but each water company will add on these external costs.
So this is around
different.
some that includes the indirect and social costs?
Yes.
Okay.
Charles, I'm going to ask a question. What percentage of the mains are cast iron? So what percentage of the mains within the UK are cast iron? And I take it, as and when they get replaced, and the companies such as Thames Water, Wessex Water, will replace these?
I don't know the answer to that. It does vary very much between different water companies.
Okay.
But I think the key thing to remember is that with large bands of trunk mains, you don't really want to have to replace them.
Okay.
It's a job for rehabilitation, the cost of excavation. Urban areas too, the actual buildings, the highways and traffic make it almost impossible to excavate something.
Yep.
So you should be looking at rehabilitation techniques where you put a liner in and lines make genuinely prove it will have a lifetime in excess of 100 years. So you need to be very, very careful about what you put in. Bearing in mind also that the intrusive work in an urban area does create the danger of movement, and these are old spaghetti socket pipes, so you need a rehab or technique that will tolerate joint movement.
Yeah.
The spray linings at the current time do not, so they don't last very long. Those are the things that I'm worried about. Don't
Okay.
replace, rehab, choose your rehab to last.
Okay. And Julian, how would you tackle a cast iron assessment and then actual replacement?
Yeah, sure. So you've got to remember that I'm on the waste side, not the rehabilitation side.
Okay.
We do gross metal loss. Some things John been talking about to ascertain the diffusion of wall thickness and work out the longevity that way. And I agree that the PE pipe, swage lining, roll down, those type of interventions work for us. I would be interested to know what you think about high build PU spray lining, for example. Have you done any work on that?
I know we've looked at this sort of work. I'm not at all convinced that that will tolerate joint movement. I think it will fail. I'd like to see, I mean, there have been no real programs of research into the testing of these lines. They're very attractive, they're very quick, in and out in next to no time, but do they last? And when you get to big diameters, you can't afford to come back. So I'm not, I've never been, ever since we were privatised, we were told we had to start rehabilitating and we had to use concrete because it was quickest and cheapest. And then we had to use resin because that was even quicker and cheaper. I have never been an advocate of this. I've never seen these lining processes that last to my satisfaction.
Well, I'm happy to have a word with you there, and that is with spray linings.
John, could you speak up, please?
Yeah, sure. I'm happy to add a word or two on the question of spray linings. Up to a certain size, the key thing is the ring stiffness of the lining you apply. Above that size, it's very much around the adhesion you can get to the actual host pipe. So I'm very much in line with Charles on the larger diameters, but there are a whole range of problems. On the smaller diameters, where it's based more on the ring stiffness, I think there is scope for their use.
That concurs with what we have, really, because I spent, like many of the water companies, we were using rapid set PUs for stability problems. We weren't looking for structural. The high builds came out later from Code 1, etc. Now 3N. And I just wondered, were there any failures in it, with those PUs because of the stiffness, that sort of thing? I don't know whether it's being done in the UK anymore, is it?
It's certainly been done on smaller diameters and not anymore on larger diameters. And that ring stiffness equation really begins to fit in somewhere above 150 mil. So that to me is more or less a natural limit. Unless you can clean the pipe and get high levels of adhesion, but even then, as Charles says, if you've got joint movement, you've got to know you can withstand that.
Now, I would add also, hesitate to use the word glue because civil engineers don't like that. It's adhesive. But as an electrical engineer, I have grave suspicions about glue, and I've never believed you could get any lining to adhere to a wet, slimy surface, and you can never dry these surfaces absolutely. I always regard adhesive properties. If your technique requires adhesion, I wouldn't consider it.
Okay. Any other questions for the guys at the moment? Ian?
Just a question to Charles. The paper was really interesting about the
Steel doesn't seem to give us the same sort of problem. We don't normally have defects within the bore. I don't think, sorry, steel and ductile. We have had problems with ductile. When ductile, it's a bit like the introduction of PVC. Actually, it was pretty disastrous when it first came out. But ductile, we thought, was fantastic, and it is very strong and very tough material. Unfortunately, when it first came out, it wasn't all that clever in aggressive soil conditions, and we lost in Wales, particularly where we had a lot of Wales farms were covered with sheep. It was generally covered with coal slag from blast furnaces. The soil is very unpleasant, and we would actually, until we adopted the technique of wrapping the ductile in plastic, we lost a lot of ductile mains within sort of 7 or 8 years, which took people a bit by surprise. Provided you protect the outside, we don't seem to have problems with ductile.
I've got a question for Chuck.
Yep.
With ElectroScan, we've looked at the way it works with pipes. It's worked very well. But in a lot of our private pumping stations, which we're bringing up to date now, would it work on chambers? Does it work on cylinders? What's the size, the maximum size it goes to? Is it something that is only really up to a certain size, 2 to 5 pipes? Because we get a lot of chambers that are fiberglass, plastic, or whatever, and the annulus goes obviously around it because of they break the joint. Could you use that on cylinders and chambers? Is it possible to probe up to measure any defaults in that side?
Yeah, one of the models that we use, great question. So the question is, can this be applied to a chamber, manhole and entry devices? And one of the things that in our models are so sensitive, that we use, people know what AutoCAD is and SolidWorks. We use ComSol. It's kind of a SolidWorks on steroids. And what we've found is we need to make sure that the current is actually in a close proximity to the wall, and also powerful. So 2 major things that we've done over the last 2 years is, one is we've reworked all of our internals so that we can vary the amount of electric current. And the second thing we've done is we've now created sheaths that will basically almost like a wire brush, get closer to the side of that. So the thing is, it's almost like the panoramic cameras that are able to, you just lower down and drop through it. As long as we can safely submerge that, so plug both ends of the inverts and fill that with water so we've got that connection. So we're more than likely, we use San Francisco as a big guinea pig. They've got a bunch of things like that. So we're more than likely going to be testing that on the next year, so that we finally have something for manholes. We have a lot of manholes that are getting redone, with a lot of different methods. Yeah, and so that's on our to-do list.
Yep.
Another question for Chuck. We kind of hinted a little bit around the performance of water cure and UV cure CRPP systems. You've probably built up quite a lot of experience now, and all like most of the older CRPP will be heat cure. But are you seeing a difference in performance between heat cure CRPP and UV cure CRPP?
Yeah. So again, it's so not all CIPP is the same, and you not only have different methods for curing, but the resins themselves, and then these are these are like cocktails that you're mixing out in the field. So not only are you looking at a felt liner versus some other liner, but you're looking at the differences of combining those various things down there, and then getting even a temperature curing, as you're saying. So I was looking even on the Houston project where we had to find it fixed. This is back before in situ form was big. We had mom and pops doing in situ form licensing in Houston in the 1990s, and it seemed like the type of work that they went in to there was maybe a little higher quality. In the States, we're seeing crews that are being asked to do 2 and 3 times the production, maybe even rushing through that curing and cooking process. And as we've done comparison, we've actually done side-by-side comparisons of upstream from this manhole was a UV liner, downstream was steam, and then 2 blocks over was an old boiled water. And we need about 1,000 more of those to really look at it. I spent 2 weeks in Germany going with Per Arsliff, doing that on a number of different types of liners. We distinctly saw improvements in UV. It's higher priced, and what we're finding is some parts of the United States are writing in only UV liner because they've had some issues. And again, I don't believe it necessarily is the liner itself. I think a lot of it has to do with how it's put in the ground. Even with UV, we just got done doing a large UV product, and I know the city wasn't happy with it. And the UV lining contractor said, "Well, look, I can't second guess it. Let me go to your next one. I want to see how you're doing." And just from the get-go, that contractor wasn't following the prescribed procedures of the manufacturer, cutting corners, doing various things, and so there were some issues with that. So it's a real partnership between the manufacturer of that liner and the contractor that they have. And we're now having some lining companies that want to have ElectroScan just as an early warning device, because within 20 minutes of finishing the line, they can see how that contractor was done just internally, so nothing blows up in their face. They'd like to see it rather than hear about it from a client. So I think what you're going to see is you're going to see people, if we find more and more felt liners that have an issue, and maybe this lowering of this 50-year useful life that we conveniently hear all the time, I think you're decidedly going to move up to even more costly methods, epoxies, liners that do a better job, and it's value for money. So you're going to get a better pipe at the end of that.
I've got a question to sort of add on to that, Chuck. Your technology is emitting frequencies of waves, and the way that it's going around and picking up defects. Are you able then to add another frequency or something, another way of measurement, so that we can trace that from above ground, so that we can locate the pipe accurately, whilst so you can say your defect is not just a chainage, but now it's actually in real world coordinates?
Yeah. So the platforms that you have in there, and we do have products that are just starting to do entry into the water business. For a long time, we needed to enter a pressurized valve or hydrant. So and those apparently have water in all the time, so that's a little better. So even in that device, these are platforms, and technology is shrinking so many of these things. So our water product not only has ElectroScan, we've got an acoustical just to see what was there before. We have temperature. We're looking at maybe even some pH balances as we go through that pipe. We put a TD camera on there as well, not to really necessarily see, but from a navigational standpoint, I need to know where 0 is in a line. So if I'm entering a pressurized valve or hydrant opening, and I've got to get to the main, I need to know where 0 is, so if I'm moving left or right from that point, I know where that is. We're already using the same footage encoders that TD has done. We don't measure the alignment of the pipe. That's a great thing for TD. So we're looking at having intermediate monitors on there so that we can actually understand that, and if we can fix the position so it doesn't turn, then we've got a serious chance of knowing the exact clock position for them. So I think we're still in our early days of additional things to add on. That's going to be more data. Certainly with video, as much data as that. My goal, as everybody's, I know, is to be in your bathrobe at home and see the information real time, so you don't have to go in the office, right? So I just kind of put myself in those shoes and see can we get that data and does that make sense?
So just to follow up on what Luke asked you, how difficult do you think it will be for you to actually combine some sort of system that will then be able to give them coordinates where the frequency comes from, where the wave is picked up?
Yeah, the GPS is actually, we're trialing things right now. So it's not in our current version, but possibly we'd be showing it to people this time next
Do you think once you had something like that, you could actually reverse engineer that, then actually map a whole kind of network of pipes that aren't mapped?
Yeah.
Actually use it as a mapping device.
Yeah, that's part of the issue with water is, hey, we don't know if it goes that direction or not. So, water kind of just tell us, look, we want a GPS on there so that we can at least locate, where that is underneath the surface and decide where that is. Even some of the more congested cities like LA and New York, they almost have to have that as a reason. So, I can't give you a date on that just yet, but initial tests have been very, very good.
Do manhole covers give different signals? You get different signals if it's a manhole cover?
No. It's we thought, gee, metal in there or a cast iron, that's gonna influence that somehow. And since this is basically a pretty focused from less than a centimeter at a time as we look at that, either if we're going down a chamber or through that pipe. It's not something that's ever been a problem.
I've got one for Julian. The first sensor that you showed us, that was the floating sensor that you had brought in from Australia, and Chuck sort of answered it from his point, but what other sensors or measurement information would you ideally like from that unit? What was missing?
Well, it's really what's possible, and we would like to be able to put the extensometer onto a floating platform, but I can't see it happening in the next few years. It's already got the ability to get for gas monitoring, H2S, etc. I can't think anything else we need at the moment.
Okay, so it's coordinated, or you just presume that it's a straight line from entry point to exit?
No, the platform will take curves.
Okay.
It's just down to the winch wire cutting into any bends. We don't want too sharp a bend. We don't tend to get sharp bends in our tunnels. So that's not a problem. The fact that we can pull it 4 kilometres just amazes me in a few hours.
Yeah.
And the hardest part is getting men into the tunnel if you find something wrong.
Okay.
Just picking up on that point about winch wires, when you are doing rehab with PD, die drawing, for instance, you're talking about very high tensions, and therefore you can quite seriously groove the side of your main while you're pulling the pipe in and the liner in. Provided the liner is a fully structural lining and will sustain the pressure for the future, even if the cast iron fails completely, it doesn't matter too much. But you do need to take it into account. And the other thing is that there's a lot of talk about a need to use cured-in-place liners because of the footprint that is required for large PD insertions. But if you use roll down, you can actually insert relatively small lengths at a time because it doesn't recover. You don't need the tension on to keep it. You can have a relatively small footprint. You can put 24-metre lengths in at a time, stop and weld another one on. And the problem we have with that technique is the biggest liner we can do at the moment is about 600 millimetres. The Americans have a system that would enable us to go up to a couple of metres without any problem. Nobody at the moment is prepared to fund bringing that machine over here for a trial. I would strongly recommend to you that you consider roll down of PE as a viable, relatively small footprint rehab technique.
You know, Charles is dead on because what we're saying, I was just at the gas show, and the technology fusing PE that is so incredible. You know, a product like ours, you know, that can go to a gas main, you know, and find defects. You know, point blank, pipes that are being put in today, PE, fused with the correct, with the most current technology, are virtually impenetrable. What the gas companies are worried about, you know, in the U.S., 50% have now turned into plastic. What they're worried about is the plastic that was put in from like the 1950s to about 5 years ago. You know, because that's where there wasn't proper fusing. It was pretty Wild West of those guys. So, you know, just fusing together pipes, and I see this when so many people are calling me up and say, look, you know, we'd like you to pre-test our pipes, and they've got a great pipe. Only, you know, the guys trying to glue two ends together really didn't get a big enough stick, you know, to put it in and to really create that. So they've got major defects, and it's bad for them because, you know, San Francisco is really looking at trying to manage down to zero, and you know, so they've got a real high standard because they don't want to have to go back in 10 years and fix the same pipe twice. So, you know, I think PE is going to be has been really fighting the whole, you know, quickness and cheapness of liners, and I think they're coming to a point to be quite competitive and you know, less of a hassle.
Yes.
Julian West from Solihull. The question towards Julian. We're in the business of not only relining rehab, but also we make OEM, the original gaskets and pipelines. And part of the work we're looking at is looking at embedding sensors into the possibility of the gaskets for OEM, original pipelines. And it's a real struggle because we all live in a commercial world. And can you see, or can you imagine a drive from above that would actually, is that a useful thing to be looking at and doing?
Actually, in relation to rising main, force main liners?
Well, pipelines in general, both sewer and pressure pipelines. The technologies there put sensors into gaskets that not only you can measure pressures and bits and pieces of the gasket, but what you were saying about actually mapping and having data points in a pipeline, it's not just the old pipeline but here, it's new pipelines that are going in.
Yeah, I think, you know, we'd like to explore that. I mean, people have come to us about putting microchips in liners so that we can scan them to find out when they were put in. And they ignored the fact we've got a fantastic GIS system, you know. So something that doesn't need invented. But yeah, we're most interested at the moment in seals for the rising mainliners. The rising mainliners are relatively new to England for sewers. I say relatively new because they've been around for 40 years, and maybe 100 have been put in the UK, but most of it's been done in Germany. And IKT have got the German government on board to do a new research project which starts in the spring next year on rising mainliners, where we're going to take landings samples from around the world and test them for all the electromodulus and strength and all the fatigue and cyclic loading. And so I think that's a really wonderful chance to explore all avenues which are associated, and maybe one of yours if you send me some details, I'll. I mean, I don't know you. I know the guy from Holland. Is it Niels Pui? Got a guy over in Holland.
Yeah, Niels and stuff. Yeah.
Maybe we could get together sometime. Yeah.
That's restricted on size, though.
On size?
On site diamonds, you wouldn't be mining them, pushing off.
Oh yeah, yeah. No, I mean, no, we're talking about the bigger assets. You know, when they go bang, we're all going to have problems, aren't we? And I mean, recently I talked to some guys in Thames, and they told me about how you were doing gross metal loss on a rising main, and there was a leakage from a piling close by, and the electricity leaked in and corroded the pipe in that local area. You know, you wouldn't imagine, would you? So that's how vulnerable your assets can be.
We get a lot of personalised, and they tend to. So that's a big issue. It's a positive.
Right, we've got time for one more question, if there are any. No? Well, I would firstly like to say thank you to all the speakers. There have been 4 brilliant talks today on 4 very good subjects. So we're going to break for lunch. We're going to come back here for 2 o'clock. So maybe feel free to walk around the museum and use this time to explore. Can we put our hands together for the guys? Thank you.